Hello. So, lesson 3.4 is talking about zeros of polynomial functions. And just like always, feel free to pause the video and or send me any questions that you might have. So, again, zeros are the same thing as the roots or the solutions. So, we're going to go ahead and look at the rational zero theorem. So, if we have a polynomial function, um, so if f of x has integer coefficients and p divided by q, where p divided by q is reduced to lowest terms, is rational zero of f, then p is a factor of the constant term a sub 0, so this one right here, and q is a factor of the leading coefficient a sub n. So we're going to use this to list all possible rational zeros of this polynomial function, 4x to the power 5 plus 12x to the power 4 minus x minus 3. So what we're going to do here is we're first going to take the constant term right here, which in this case is, sorry, that's an A, is negative 3. And then we're going to find the leading coefficient over here, which for this one, so it's a sub 5 because it's the fifth power, is going to be 4. So what we're going to do now is we're going to find factors of negative 3, which are positive and negative 1 and positive and negative 3. So this is our p. P is a factor of the constant term. Or these are our p's, like options for p's. Now, factors of 4 would be positive and negative 1. And that would be, the other one would be positive and negative 4. 1 times 4 is 4. Negative 1 times negative 4 is 4 as well. And the other factor would be positive and negative 2. And these are these are possible q's. So q is the factor of the leading coefficient. Okay, now we're going to go ahead and use this p divided by q. So p divided by q. So that means that we are writing the factors of negative 3 and dividing them by factors of q. So positive and negative 1, positive and negative 3 divided by positive and negative 1, positive and negative 2, positive and negative 4. Okay, so possible, again, this doesn't mean that all of these are possible rational zeros are, we're going to take the 1 and divide it by 1. So it's going to be positive and negative 1, and this is going to be a set. So we're going to put it inside braces. Then we're going to take 1 divided by 2, and we're using still positive and negative. So 1 divided by 2 is going to be a half. 1 divided by 4, so positive and negative 1/4. And now, since we divided the 1 by everything that's under, we're going to take the 3 and divide it by the same numbers. So positive and negative 3 divided by 1 is a 3. Positive and negative 3 divided by 2, and positive and negative 3 divided by 4, or 3/4. And we close that. So these are our possible rational zeros. And again, the key word is possible. So they're not necessarily all the rational zeros. Okay. And again, our example says list all possible rational zeros. Now, the difference between this and the previous example is that this one says find all zeros of fx equals x cubed plus x squared minus 5x minus 2. So what we need to do here, I just want to check that which colors I used. We're first going to go ahead and figure out what our constant is. And our constant here is -2. And our leading coefficient, it's third power, so it's a sub 3, is going to be 1, because there is no number, so that's the understood 1. So this is our Q, and this is our P, or the factors are going to be. So next what we're going to do is we are finding the possible rational zeros here. So again, P divided by Q. We're listing all the factors of -2 first, and those are positive and -1 and positive and -2, because 1 times 2 is 2. 1 times -2 is 2, and -1 times positive 2 is 2. And then we are dividing it by the factors of 1, which are positive and -1. Okay, now we're going to do the division here. So positive and -1 divided by positive and -1 is going to be positive and -1, and positive and -2 divided by positive and -1 is going to be positive and -2. So we have 4 options. We've got positive and -1, and we have positive and -2. Now, since we need to find all zeros, we're going to go ahead and pick one of these numbers. Remember, these are the possible rational zeros. We're going to pick one. Just randomly pick one. Let's start with the number 1. Now, we learned in the previous lesson that if we divide by the our polynomial by the rational zero, we know that it's going to be a 0 if the remainder is a 0. So we're going to pick, I said 1, and we're going to do the synthetic division here. 1 is the leading coefficient. 1 is the coefficient for x squared. -5 is the coefficient for x, and then -2 is the constant. We're dropping down the 1. 1 times 1, we multiply those. 1 times 1 is 1, and then we add 1 plus 1 is 2. 2 times 1 is 2. -5 plus 2 is -3. -3 times 1 is -3, and -2 plus -3 is -5. Okay, we had a remainder. So because of this, we know that 1 is not a 0. This needs to be 0. So the remainder has to be 0. So there shouldn't be any remainder if it is a rational 0, if it is a solution. Okay, so let's pick another number. Let's do 2. our polynomial function, the leading coefficients are obviously the same. And we're bringing the 1 down. 1 times 2 is 2. 1 plus 2 is 3. 3 times 2 is 6. Negative 5 plus 6 is 1. 1 times 2 is 2. Negative 2 plus 2 is a 0. Well, since our remainder now is a 0, we know that 2 is a, excuse me, is a 0. It is a solution of the function. So since 2 is a 0, we know that our factor is going to be x minus 2. The other factor comes from these coefficients. So x squared, we do 1 less than the original polynomial function because we took out an x, plus 3x plus 1. Okay, so, and then x minus 2. So these are factors of our original polynomial. Now, we need to set these to equal 0. Well, we already know that this is going to be, x minus 2 is going to be 0. So x is 2. We already got that here because we used it for the synthetic division. We need to go ahead and factor x squared plus 3x plus 1. What we're going to do is we're going to use the quadratic formula for that. So x equals negative b plus minus b squared minus 4ac inside the square root divided by 2a. So plugging in the numbers, negative 3 plus minus 3 squared minus 4 times 1 divided by 2 times 1. When we simplify this, we get x, not x, so x equals negative 3 positive and negative square root of 5 divided by 2. So those are our other factors. So our factors for this are going to be 2 right here, and then these two. So negative 3 minus square root of 5 divided by 2, negative 3 plus square root of 5 divided by 2. Those are all our zeros. Again, on the previous example, we found the possible zeros. This is where we found all the zeros. Okay, next we're going to look at properties of roots of polynomial equations. So if a polynomial equation is of degree n, then counting multiple roots separately, the equation has n roots. Again, remember that this is the same, the word roots is the same thing as solutions or as zeros. So all of these go hand in hand. Now, if a plus bi is a root of a polynomial function with real coefficients, b does not equal 0, then the imaginary number a minus bi is also a root. So imaginary roots, if they exist, occur in conjugate pairs. So again, it's a plus bi and a minus bi. Both are going to be roots. If one of them is a root, the other one is going to be a root. Okay, so next we're going to look at this polynomial function. So that is a fourth degree polynomial function. Now, if we look at number 1, again, the degree is 4, so it has 4 roots. Now, we're going to look at all the possible rational roots first. um, P over Q, and P is the, or are the factors of the constant. So 13, so positive and negative 1 and positive and negative 13. We divide that by the leading coefficient, which in this case is 1, so positive and negative 1. So when we do the division, our options are possible rational roots are positive and negative 1, positive and negative 13. Okay, next what we're going to do is we're going to go ahead and use the synthetic division. Again, we're just going to pick a number out of one number out of these. I'm going to use 1. That's an easy number to start with. 13, trying to multiply with 13 is kind of a lot. Our coefficients are 1, negative 6, 22, negative 30, and 13. Again, make sure that they are in descending powers, and if there's any terms missing in between, you need to put a 0 over there. We're bringing the 1 down. 1 times 1 is 1. Negative 6 plus 1 is negative 5. Negative 5 times 1 is negative 5. 22 minus 5 is 17. 17 times 1 is 17. Negative 30 plus 17 is negative 13. Negative 13 times 1 is negative 13. And when we add those, we get a 0. Well, look at that. We got lucky with that one. So the first one is, so 1 is a real root. Okay, so our original polynomial x to the power 4 minus 6x cubed plus 22x squared minus 30x plus 13 has factors of x minus 1, that comes from here, and then the other factor is x cubed. Again, it's 1 less than the power of the original one, minus 5x squared plus 17x minus 13. Okay, we again have a cubed, so we have a polynomial here, not a quadratic function like, um, or quadratic, yeah, not a quadratic like we had in the previous one where we could use the quadratic formula. We're going to restart with this one now. Or do the same thing, x cubed minus 5x squared plus 17x minus 13. So we're going to go ahead and list the possible rational roots for this one. So again, the constant, positive and negative 1, positive and negative 13, divided by the leading coefficient factors, positive and negative 1. So we've got positive and negative 1 and positive and negative 13. These are, again, possible rational roots. We're going to pick something. We're just going to start with the 1 again because it's an easy number to start. And this is the one that we are using. So 1, negative 5, 17, and negative 13. We bring the 1 down. 1 times 1 is 1. Negative 5 plus 1 is negative 4. Negative 4 times 1 is negative 4. 17 minus 4 is 13. 13 times 1 is 13. And again, look at that. We have a remainder of 0, so 1 is a real root. So x equals 1 means that it's going to be x minus 1 equals 0 is one of the factors. Okay, so what do we need to do next? So we got to the point. So our original equation is this one right here. We figured out two factors. We figured out that it has an x minus 1 and it has an x minus 1. Look at that. There's two of them. Excuse me. And then we have this factor here. x squared minus 4x plus 13. Okay, we need to factor this one right here. I might need to continue factoring on the last page. I don't have enough room here. X squared minus 4x plus 13. So I'm going to go ahead. I need to write something so that it gives another. So hold on, what page was that? That was page 3. Page 3, example, continued. Okay, so it was x squared minus 4x plus 13 equals 0. So our A here is 1, B is -4, and C is 13. I didn't do this with the previous one, but we're using the quadratic formula again to factor because there's no, if you look at this, there's really, you can't factor it without it to A. So x equals -4 plus minus -4 inside parentheses squared minus 4 times 1 times c, which is 13. All this inside a square root divided by 2 times 1. Okay, so when we simplify this, we get -36 divided by 2. Okay, so 4 plus minus divided by 2. 36, square root of 36 is a 6, and the negative square root of -1 is an I. So we can see that we have an imaginary root here. Well, we can still divide by 2, so we get x equals 2 plus minus 3i. Now, with this, we have the conjugate pairs. You have to make sure that 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 those both are here. When we do the quadratic formula, we'll have them automatically because it's plus and minus. So 2 plus minus 3i. So that's conjugate pairs. So our solution set is going to be 1 and 1 and 2 plus minus 3i. Now, if we look at, we've got 1, 2, 3, and 4 roots, right? And we had a degree 4, which means that we've got 4 roots. So we know that we have all the roots here. Even though we've got the 2, 1 and 1, that would be, you know, multiplicity of 2. But we know that we have both of those. So you want to make sure that you've got enough roots. Whatever the highest degree is, you should have the exact same amount of roots. Okay, next one. What we're going to do is we're going to look at the fundamental theorem of algebra. So if f of x is a polynomial degree n, where n is greater than or equal to 1, then the equation f of x equals 0 has at least one complex root. The linear factorization theorem, so if f of x is a polynomial function where n is greater than or equal to 1 and a sub n, so the leading coefficient does not equal 0, then we can factor it like this, where C1, C2, Cn are complex numbers, possibly real and not necessarily distinct. Possibly real and not necessarily distinct. So in words, an nth degree polynomial can be expressed as the product of a non-zero constant and n linear factors where each linear factor has a leading coefficient of 1. Okay, let's look at our example. Finding a third degree polynomial function with real coefficients that has -3 and I as zeros and such that f of 1 is 8. So we're going to use the linear factorization theorem here. F of x equals a n x minus c1 x minus c2 times x minus cn. So it's a third degree polynomial, which means that our n is going to be 3. Our one of the factors is -3. And now remember when we are saying, or one of the zeros. So when we say that a 0 is -3, when we write it as a factor, we bring it to the same side as the x, it switches the sign. So this is x plus 3. Our next factor is going to be I. So x minus I. And since we have that, x minus I, we know that the conjugate pair is going to be a factor as well, x plus I. Okay, we do have 3 factors. It's a third degree, so we should have 3 factors here. Now what we're going to do is we're going to go ahead and FOIL FOIL these two. We're leaving the x plus 3 for now. So when we FOIL, I'm going to do x minus I, x plus I on the side here so that I have enough room. So first is going to be x squared. Outer is going to be plus ix. Inner is minus ix. And last is going to be negative I squared. Well, these two cancel each other out, x squared and negative I. So I squared is a -1, and then we have the negative in front of it, so it's going to be x squared plus 1. So and this is why we did the foiling of the conjugate pairs first. Now we're going to go ahead and FOIL these two. So we get a sub 3 x cubed plus x plus 3x squared plus 3. Okay, now how do we move forward? We are still missing the leading coefficient here. What we're going to do is we know that f of 1 equals 8. So we're subbing in the 1. So f of 1 equals a sub 3, 1 cubed plus 1 plus 3 times 1 squared plus 3. And all this should equal 8, like it says over here. Okay, so what do we get? We get, when we do the parentheses, we get 8. And then we divide by 8, so we get a third, so our leading coefficient is 1. So now we're going to go ahead and plug it in. Our leading coefficient is 1. X cubed plus x plus 3, x squared plus 3. We are distributing the 1. Well, of course, it doesn't change. What I do want to change, though, is the order. I'm going to bring this. X cubed is the highest. 3x squared is going to be the next one. And then we're doing x and 3. And that's our answer. Okay, next rule that we're going to look at is the Descartes' rule of signs. Let f of x equal this polynomial be a polynomial with real coefficients. So the number of positive real zeros of f is either a, the same as the number of sign changes of f of x, or less than the number of sign changes of f of x by a positive even integer. If f of x has only one variation in sign, then f has exactly one positive real zero. Okay, the number of negative real zeros of f is either the same as the number of sign changes in f of negative x, or less than the number of sign changes in f of negative x by a positive even integer. If f of negative x has only one variation in sign, then f has exactly one negative real zero. Okay, so what does this mean? Let's go ahead and look at an example here. So determine the possible number of positive and negative real zeros of this f of x that we've got. So again, f of x, possible sign changes lets us know the positive real zeros. Okay, f of x is x to the power of 4 plus, not plus, minus 14x cubed plus 71x squared minus 154x plus 120. Okay, there's a sign change right here. There's a second sign change, a third, and a fourth one. So we have 4 variations in sign. It all comes from how many sign changes there are. Positive, negative, positive, negative, positive. So the number of positive real zeros is the same as the number of sign changes or less than the number of sign changes of positive even integer. So it can be 4. The next positive even integer less than is going to be 2, and then there's the 0 as well as if possible. Okay, next we're going to look at f of negative x. Possible sign changes means that there are negative real zeros. Again, remember that we're not looking at for the real zeros, we're just looking at how many are possible right here. Okay, so we're going to rewrite f of x as f of negative x. So f of negative x is going to be negative x to the power of 4 minus 14 negative x cubed plus 71 negative x squared minus 154 times negative x plus 120. Okay, now this will stay as x to the power of 4. This will become 14 because negative x cubed is going to be a negative still with the odd exponent, and then we have a negative in front, so two negatives become a positive. Negative x squared is going to be a positive, so 71x squared. A negative and a negative is a positive, 154x plus 120. Okay, now if you look at this, there are no sign changes. All of them are positive. So no variations in sign. Every single sign is positive. So that means that there are no negative real zeros for f, or f of x. Okay, that's it for this lesson. Again, please don't hesitate to contact me if you've got any questions. Bye.